All right, so this section, section 31 is on linear approximations. All right, so I have a little sketch of what we're going to do today, guys. So we have, some kind of curve, some kind of original function. And basically, if you take any curve and let's say we graph it on our graphing calculator, and then we hit zoom in, zoom in, zoom in, zoom in, zoom in. If you zoom in enough times, it's going to look like a line. Exactly. So that's what we're going to talk about. So it's going to look, so it says you can find a linear approximation for the curve by finding the equation of a tangent line, right, at a good point. So we've done that many, many times before, right? I've asked you since the beginning of the year, how do you find the equation of a tangent line, right? So we've done that before. So for instance, maybe I want to find a close approximation for the cube root of 7.8 without using a calculator. So you don't have a calculator, but you need a close approximation. You can use the equation of the tangent line at 8.2 to do this. So basically, if you have 7.8 and you want to know what its y value is on the curve, instead, we use the point that is directly above it along the tangent line. Does that make sense? And they're going to be super, super close to each other. Does that? I don't know. All right, we won't do that example, but we'll try some other ones. So it says there is a somewhat complicated formula in your textbook, but I always just want you to remember how to find the tangent line of an equation. So we've done that many, many times before. You might hear different words. You might see linear approximation. You might see something where it says find the linearization. And things like that. Does that make sense? So you might see it phrased in a certain way, but every time you see something that says linear approximation, linearization, or whatever, what it means is use the equation of a tangent line. Okay, so let's try this one. So it says find the tangent line approximation of f of x equals 1 plus sine of x at the point 0, 1. All right, so if we're finding the tangent line, we need to know the slope and the point. So we have the point. We're going to get the slope from the derivative of this. So we're going to do f prime of x is equal to 0 plus the derivative of sine is cosine. And we're going to use x equals 0. So I have cosine of 0, and cosine of 0 is 1. Okay, so that means that our slope is 1. Our point, we said, was 0, 1. So we have a slope of 1 and a point of 0, 1, right? We have y minus y1 equals m times x minus x1, which really, if you were quick, you would have realized, oh, wait, that's my y-intercept. So I really just get 1x plus 1, right? So what textbooks will usually do is they call this the linear approximation or the linearization. So they write it as L of x is approximately 1x plus 1. So I don't care if you do L of x, or you could even do f of x, that's fine. Just use the little approximately sign, so you could have f of x, but it's going to be when x is near x equals, in this case, x equals 0, right? So whenever you're near an x value of 0, that's the linearization. I don't know why I did capital F of x. Definitely don't use capital F of x, use lower. Okay, that would be antiderivatives, right? We talked about that before. All right, so if I want to find an approximation for f of 0.23, then instead of going back and plugging into 1 plus sine of 0.23, I have no idea what sine of 0.23 is, right? We don't know what that is. We plug it into this linear approximation. So I have 1 times 0.23 plus 1, so I get 1.23. All right, so get your calculators out. Let's do a couple different things. Okay, so the first thing I want you to do is actually find f of 0.23, which is going to be 1 plus sine of 0.23. So make sure you're in radian mode. So when I do that, I get 1.227977524. Okay, and it's pretty close. If I was rounding to 2 decimal places, I would have it, right? 1.23. So it's pretty close. And then the next thing I want you to do is I want you to graph under your y1 and y2. I want you to make y1 1 plus sine of x. And I want you to make y2 1 plus x. Okay, and I can do that on here too. Maybe. So go and try it with me. So our linear approximation was what? X plus 1, is that right? Okay. Make sure I'm in radian mode real quick. Yep. All right, so we get this curve. So that's what 1 plus sine of x is, just sine of x just shifted up 1. And you see how that line goes right through it? Okay, so if I'm at x equals 0, that portion of the curve looks just like that line. And you could zoom in. So if I hit zoom in, yeah, you can use your Z box too. Do you guys like the Z box now? Right, see how it looks like a line there? I mean, the more we zoom in, the more it's going to look like a line. So it looks like a line for all values that are really, really close to x equals 0. That's what we're doing. Okay, so that's why we were able to use a line to approximate. Does that make sense? All right, so let's try another one. So it says, find the linearization of the function f of x equals the square root of x at the point 4, 2. Use it to approximate the square roots of 3.98 and 4.05. Are these approximations overestimates or underestimates? Okay, so our function is f of x equals the square root of x, which is x to the 1/2. So when I take the derivative, I get 1/2 x to the negative 1/2, which is the same as 1 over 2 root x. So many of you guys would be able to just jump to that, right? Our point that we're using for our approximation is 4, 2. You're never plugging in like a decimal into the slope, right? Because to find the slope, because it's always going to be something that's very easy to find. Okay. So I'm going to find f prime of 4 is going to be 1 over 2 root 4, which is going to be 1 over 4. So we're going to have y minus 2 equals 1/4 times x minus 4. So we had our point and we had our slope. So we used it to write it in point slope form. So we get 1/4 x minus 1, and then I'm going to add the 2 over. So I get 1/4 x plus 1. Okay, that's our linear approximation. So you can write it as f of x or L of x, but use the approximation signs, right? So I'll call it L of x. All right, so if I'm finding the square root of 3.98, instead of plugging, finding the square root of 3.98 on my calculator, what I could do is 1/4 of 3.98 plus 1. And you can do this without a calculator. In the first period class, they were like, well, I don't know how you expect us to do that. Yeah, I do. Like, you can do it without a calculator. My husband taught it last year in 2nd grade, right? 3.98 divided by 4. Would you be able to handle that? Okay, but for our notes today, I will let you use your calculator to do it quickly. All right, so if I have 3.98 divided by 4, and I add 1 to it, I get 1.995. Okay, so kind of treat your calculator like an I-step calculator. Don't do the square root of 3.98 and all that. Just like a basic little type. All right, so if I have the square root of 4.05, I get 1/4 of 4.05 plus 1. So again, 4.05 divided by 4 plus 1. So I get 2.0125. Okay, do those seem reasonable for the square root of 3.98 and 4.05? Yeah. And if you actually find them, they are super, super close to that. Okay, I think they're up to 3 decimal places, or almost 3 decimal places. What are you saying? Right, that's why they invented this, right? To approximate things without using a calculator. But it's also handy for things that maybe, I don't know, it's like difficult to plug in. Yeah, I mean that I guess without a calculator, yeah. But so back in, I'm trying to think of like a use for this. So back when I was in high school, we didn't actually use our calculators in geometry. We used sine and cosine and tangent tables, right? And it had all of these decimals for sine of whatever, cosine of whatever. So that would be an application of this. Like, it's an easy way to get those tables. All right, so use this equation to approximate the square root of 25. Is this close to the actual value? Explain why or why not. All right, so if I'm doing the square root of 25, and I'm using 1/4 x plus 1, right, that linear approximation I just had, and I plug in 25, I get 6.25 plus 1, which is 7.25. Is that close to the square root of 25? No, not at all, right? Yeah, exactly. So explain why or why not. Why is this not super close? Right, it's not, but why is it not the tangential value as you're calling it? Huh? I wasn't finding the tangent line I was finding the tangent line before at 4, 2. What do you mean by that? No one can come up with this.
If you're taking the tangent line of the function at the point on the curve,
Mm-hmm.
in fact, the function, the graph of the function changes over time.
It does. Yeah, so what's wrong with this then? Yeah, Andy.
Find the line at x equals 4.
Exactly. That's exactly what I'm trying to get at. Do you guys understand? So we found the equation of the tangent line at x equals 4. So this only works near an x value of 4. Okay, we used x equals 25. So the further you get away, the further your approximation is off, right? Because if you're thinking about the curve, the square root here, if we have 4, 2, and we find the slope there, right, it's going to be close only for values that are close to 4. But as I go out like this and I go up, do you see how the further you go out, the further it's off? Okay, that's what's happening. All right, so you always have to be close to the x value that you used. All right, so it says find the linearization of this at x equals 64. So if I have g of x equals the cube root of x, I have x to the 1/3. So I'm going to have g prime of x equals 1/3 x to the negative 2/3. So really what this is 1 over 3. And since it was negative, it's on the bottom. So I'm going to have the cube root of x, and I'm going to take that result and I'm going to square it. That's x to the 2/3, right? So I need to find my slope. So my slope is going to be evaluated at x equals 64. So I'm going to have 1 over 3, the cube root of 64. Anybody know that? So I have 1 over 3, and I have 4 squared is 16. So it's 1 over 48. But we don't know our point. We know this is the slope, but we don't know our point. So we have 64 comma something. Okay. Yeah, so I need to find it. So I go back to my original and I say g of 64 is going to be the cube root of 64, which is 4. So that's my point. So I'm going to have y minus y1 equals m times x minus x1, right? So I'm going to have y minus 4 equals 1 over 48 times x minus 64. And I always have to simplify. I know, like, at the beginning of the year when we found equations of tangent lines, I never made you multiply it out. But for linear approximations, you always need L of x is approximately, or f of x is approximately this, right? You don't need anything over with it. So we have 1 over 48 x minus, they're both divisible by 16, so it's going to be 4 over 3, and then plus 4. So our linear approximation is 1 over 48x. And negative 4 over 3 plus 12 over 3 is 8 over 3. Okay. So if I want to find the cube root of 65, I just plug in 65 in there. A little bit harder to do without a calculator, so I'll let you use it. So 65 over 48 plus 8 over 3. So it's 4.02083 repeating, right? You could also find it in fraction form as well. All right, and then cube root of 61 is 61 over 48, right? 1 over 48 times 61 plus 8 over 3. Which is 3.9375. And they should make sense in the end, right? We know that cube root of 65 is a little bit more than 4, and cube root of 61 is a little bit less than 4. So we're good. Okay, would these be overestimates or underestimates? So what do we think? Yeah, because the cube root of x is a function that looks like this, right? So if I'm finding the equation of a tangent line of 64, my tangent line is above. So if I was justifying this on the AP exam, which you will have to do, it will say justify your answer, right? Why is this an overestimate? What would we say? Exactly. Yeah, so not because the function's increasing, but because it's concave down. Okay, when things are concave down, so when you have f of x is concave down, all of the tangent lines are going to be above the curve. Does that make sense? So at 64, our slope was, our second derivative was negative. It was concave down. So we're going to say f double prime of x is less than 0 at x equals 64. Therefore, we have overestimates. So it's always using concavity when you decide if it's an overestimate or an underestimate. So use concavity. Oh, it should be G. Man, I would really get docked on the AP test too. I hate when people do that. I did it. All right, thank you. All right, so next up, so try the same thing. So find the linearization of the function. Oh, what? No, not a good place. That was a crazy bounce shot. All right. All right, so linearization of the function. So I'm going to have f prime of x equals 4x cubed plus 6x. All right, and in the linearization function, they always say at a certain a value. Okay, a is really just x, so that's what Jack's saying. He says it should be x equals -1. It is the same thing, x equals -1. So we're going to have f prime of -1. So I get 4 times -1 cubed plus 6 times -1. So I get -4 minus 6. So I get -10. So that's my slope. And then my point, I know I have -1 comma, but I don't know what the y value is, right? So I need to find it. So I have f of -1 is -1 to the 4th plus 3 times -1 squared. So I get 1 plus 3 is 4. So I have the point -1 comma 4. So all it's saying is find the linearization. It's not saying to approximate whatever. So all we're finding is that L of x equation. So I'm going to have y minus y1 equals m times x minus x1. So I'm going to have -10x minus 10 plus the 4. So my linear approximation is going to be -10x minus 6. That's it. Yeah. Yeah, exactly. So you could write when x is near -1. But since it said at x equals -1 anyway, or a equals -1. All right, so number 5. So it says use a linear approximation to approximate the square root of 145. Okay, so sometimes you kind of have to pull information out of it. It doesn't tell you all the stuff that you need. Okay, can you think about what f of x would be in this situation? What function? Yeah, the square root of x, right? And what point are we going to use that's close to that? 12, that x equals 144, right? So it's going to be 144 comma 12. Exactly. So do you understand how sometimes you're not given the necessary information? You have to think, okay, what's my function for this? What's the point that I want to use? What's the nice point, right? Okay, so then we do the same thing. So we have f prime of x ends up being 1 over 2 root x. So our slope is f prime of 144, which is 1 over 2 times 12, so 1 over 24. So we have y minus 12 equals 1 over 24 times x minus 144. And we simplify, so I have 1 over 24x minus 6, add the 12 over. So my linear approximation ends up being 1 over 24x plus 6. So if I want to approximate the square root of 145, I use that. So I have 1 over 24 times 145 plus 6. And you could find the fraction value if you want, or, you know, if I let you use your calculator, you can use the decimal. So you get 12.0416 repeating. All right, does that seem close? Yeah, seems pretty good. As long as you're not getting something like 100 and you're like, wait, square root 145 isn't 100. It should be pretty close to 12. All right, so sometimes it's phrased this way. So it says use a linear approximation to approximate the solutions to x squared equals 123 and x cubed equals 123. All right, so I've put questions like this on the test before, and people have totally blanked because they don't know what the function is. Okay, so if you're finding the solution to x squared equals 123, then you're really finding the approximation for x equals plus or minus the square root of 123, right? Does that help? So what function are you using? F of x equals root x. It's just like the last one. And what would be a good point that's close to that to use?
121.
Yeah, 121 comma 11. Does that make sense? So that's just like the last one, so you guys can definitely do that one. So let's try this next one. So if I have x cubed equals 123, then I'm solving x equals the cube root of 123. So that means my function that I'm using should be the cube root of x, right? So I want something that's going to be close to 123 that I can take the cube root of. A little tricky. What is it going to be?
125.
Yep, 125, exactly. So 125 comma 5. All right, so we go ahead and we take the derivative. So we say f prime of x is going to be 1/3 x to the negative 2/3, which means f prime of 125 is 1/3, and then the cube root of 125, all of that squared. So what's the cube root of 125? 5. Yep, and then square it. 25 times 3. Yep, so we get 1/75. So we have y minus 5 equals 1/75 times x minus 125. So we get 1/75x minus 5/3, and we're adding the 5 over.
Isn't it easier just to like keep it in that form when you plug in? Then you get like a
Yeah, it could be, yeah. So we end up getting L of x is approximately 1/75x, and then plus 10/3, right?
Plus,
So the cube root of 123 is 1/75 times 123 plus 10/3. So do you guys see what Jay's saying? So he's saying it's easier to plug in x equals, like here, to plug in x equals 123. Because, I don't know, you don't have to get common denominators and all that. But, well, you do eventually. So 123/75 plus 10/3. So we get a little bit less than 5, which we should, right? So 4.973 repeating. So that's our approximation. Okay, does that make sense? All right, so this was an actual AP question a couple years ago. So it says the approximate value of f of x equals the square root of 4 plus sine of x at x equals 0.12 can be found by the tangent line approximation x equals 0. So this was on the non-calculator portion, so let's try to do it without our calculator. Okay, so we have our f of x, and we're saying we're using x equals 0 to be the place where it's close to. See how we don't want to use 0.12? Because we don't know how to do the square root of 4 plus sine of 0.12 without a calculator, right? We're trying to use this linear approximation. So I have f prime of x ends up being 1/2, 4 plus sine of x to the negative 1/2, and then times the chain. So the derivative of the inside is going to be cosine of x. So if I'm finding f prime of 0, I get 1/2, 4 plus sine of 0 is 0, to the negative 1/2, and then cosine of 0 is 1. So can you guys do 4 to the negative 1/2 in your head?
1/2.
Yeah, it's 1 over the square root of 4, which is 1/2 exactly. So we have 1/2, and then times another 1/2, which gives us 1/4. So that's our slope. All right, and then our point, we're going to use f of 0. So f of 0 is going to be the square root of 4 plus sine of 0, which is 0. So the square root of 4 is 2. So our point is 0, 2, and our slope is 1/4. So notice how that's the y-intercept, 0, 2. So I'm going to have y equals 1/4 x plus 2. So that's my linear approximation. So instead of y, I'll do L of x, I guess. So L of x is approximately that. Doesn't really matter. All right, so my approximation for 0.12, we have 1/4 of 0.12 plus 2. Can you guys do that? 1/4 of 0.12? 0.03, exactly. So I have 0.03, which ends up being 2.03. So I have 2.03 as my answer. Okay, all without a calculator. Do you guys see how we do this now? All right, last couple questions. Oh, is this the very last one? Yeah, it is this. All right, so number 8 says the table lists the amount of U.S. cash per capita in circulation as of January 1st in the given year. Use a linear approximation to estimate the amount of cash per capita in circulation in the year 2050. Is this an overestimate or an underestimate? Why? Okay, so this one's kind of weird. It's not going to give us a close approximation. So let's think about what the graph would look like. So if I did graph this all out, and I had 85 was my, starting point, and then I have 95, 2005, 2015, and then further down the line I want 2055 or 2050. Kind of funny I did 50. All right, so I want that one. And you think about graphing these points, you don't have to be like super exact, you just kind of have to think about it. 2.07, let's say it's here, then 2.95 is going to be close. 6.01 though is going to be way up here. And 1093 is going to be really far up there. Does that make sense? Do you think that this is concave up or concave down? Concave up. Okay, so if you remember when we talked about concavity, we made the definition of concave up. We had two different things for the definition. So we said a curve is concave up when the slopes of the tangent lines are always below the curve. That was the first definition. And the second definition is something is concave up if the, so f is concave up if f prime is increasing throughout the function, right, throughout that interval. Does that make sense? So if f prime is increasing, that means the slopes are always getting bigger. Okay, so you could find the slope between these 2 points, the slope between these 2 points, the slope between these 2 points, and you would see that they are definitely getting bigger. Do you guys understand that? Okay, so that would be like a justification. So the slopes are increasing. I guess I should say the slopes of, we'll call this f, slopes of f are increasing. All right, so if I want to get a tangent line approximation, I have no function this time. There's nothing that I can plug in for. So I would be forced to use the 2 points that are closest to it. Do you guys see? So you could find the slope between these 2 points, and you could continue it straight. But obviously your function is curving. Does that make sense? So we can use that tangent line, but it's going to be really far off. So is it going to be an overestimate or an underestimate? Yeah, it's definitely going to be an underestimate. Okay, so we would use those two slopes. So we'd say m equals 1093 minus 601, not two slopes, 2 points to find the slope. 215 minus 2015, 2005. Here we go. So 49.2, so that's our slope. And you can use any point. So we'd have y minus y1, we'll use the 1093, equals m times x minus x1, 2015. And we can multiply out and get our linear approximation. So we'll do what Jay suggested. So we're trying to find it at x equals what? What am I plugging in for x? Yeah, be careful though, 2050. Because if I did 2015 in my problem, I need to do 2050. Does that make sense? All right, so I'm going to find this. So I have 35 times 49.2. So this side of the equation, I get 1722. And then I would add that 1093. So you would say your cash per capita at that time is at least 2,815. So most likely more, right? Because we said ours was an underestimate. Does that make sense? So you can get things from tables as well. I know it's a little bit strange, but. All right, let me pass out your homework.